Yeah, I'm pleased to talk to you today about likelihood ratio meta-analysis. My salary is paid by the University of British Columbia, but I do receive some honoraria and stipends, all from government sources, and none of which pose a conflict of interest for this presentation today. I'm going to be making reference to a couple of papers and another researcher in particular, Stephen Goodman, and I will provide complete references at the end of this talk, but there are a couple of papers that, should you wish to explore likelihood ratio meta-analysis further, you can look at the sources that I will give you at the end of the talk. Stephen Goodman's work, very important for this topic. So let's name theta as a parameter, which is that quantity which we wish to estimate from the data. We have some options as to how we can conceptualize theta. One way is to view it as an unknown random variable, which could have many possible values. After observing data, one could then ask which possible values of theta are more likely to be true than others, given the data. Another way to conceptualize theta is to assume that it is unknown but fixed. This is the frequentist conceptualization. The emphasis is now on the sample. And if an estimate of theta is different from sample to sample, it is because of random fluctuations between samples. The catch with the frequentist conceptualization is if one uses a method which assumes the sample is the thing which is varying, and not the fixed but unknown parameter theta, then we ideally would take many samples in order to understand the nature of theta. If a researcher could redo an experiment many times, and if there was a phenomenon under investigation which was thought to have a single fixed unknown value, I'm not a physicist, but the mass of a proton comes to mind as perhaps a good example. Then the collection of many samples in an experimental setting which was ideal would be an excellent way of establishing a range of plausible values. But I would ask you to consider whether a small number of randomized trials done in humans and which are not ideal experiments, because all of the circumstances of the experiment cannot be controlled for or replicated, that if this kind of problem is really best viewed through a frequentist lens and its notion that sampling error is all that's preventing us from zeroing in on a one true fixed underlying value. If we choose a conceptual framework that views theta as unknown and therefore compatible with many possible values, then a good place to start is with a single observation. This is the so-called Bernoulli random variable, which I am sure some of you, maybe even most of you, have heard of. For argument's sake, let's suppose we are interested in measuring the probability of death over some time frame, say 28 days, and in some population exposed to new treatment. Suppose if we had an N of 1 sample, where at the end of 28 days, the individual from this N of 1 sample had survived. We only have one observation, and we can't say much, but we can say something. We can say a couple of things, actually. One thing we can say with confidence is that the 28-day probability of death is not 100% in this population, and we can conclude this because we have a survivor. The other thing we might say is that, given this one observation, and confining ourselves only to this one observation, the most likely probability of death in our population is 0%. And the likelihood of other probabilities of death decrease as we move from 0% to 100%. This curve is a Bernoulli likelihood. Now, let's instead suppose that instead of a survivor in our N of 1 sample, we had, unfortunately, a death. Again, we cannot say much about the probability of death in our population, but we can say that the 28-day probability of death is not 0% because we had a death. And the most likely probability of death in our population, given this one data point, is 100%. Now suppose we had a much larger study consisting of 2 patients, an N of 2 sample, which included 1 death and 1 survivor. We can multiply their Bernoulli likelihoods together at each possible value along the horizontal axis. That is, at each possible probability of death to obtain a combined likelihood. That's the blue line, blue curved line you see at the bottom of the figure. We can now see from our sample of 2 individuals that the most likely probability of death given these data is 50%, and that 100% and 0% are now both impossible. In an N of 3 sample, which includes 1 death and 2 survivors, for example, we can apply the same logic to show that 33% is now the most likely probability of death. We can keep adding observations time and time again for more and more patients in a similar fashion. And what we'll see is a further tightening of the range of possibilities. So you might notice that on the horizontal axis, I've shrunk it down to go only up to 11 or 12% there, just so you can see contrast. So that shape sort of appears now to be a bell-shaped normal looking curve. We have now 2,910 alive people in this hypothetical example and 88 deceased people. And when you combine all of those 3,000 individuals, or nearly 3,000 individuals, you get a combined likelihood function like you see here. So a likelihood function can be scaled without losing its shape. And here we see one that's scaled to 100%, which at its maximum value. The value of a likelihood at any single point on a likelihood function lacks a useful meaning, but the ratio of any 2 likelihoods on the function can be very useful. And this is the so-called likelihood ratio I'm referring to. In this example, I take the results from the SUSTAIN-6 trial on semaglutide and its primary composite outcome of, I think it was death from cardiovascular causes or non-fatal myocardial infarction or non-fatal stroke. I think that was the primary composite outcome. And I compare the relative likelihood of the primary outcome at the maximum likelihood estimate to the likelihood of no effect. So the maximum likelihood estimate would be the hazard ratio for the primary outcome that was reported in the trial. When I do this, when I make this comparison between what was reported in the trial to the null hypothesis of no effect, this produces a likelihood ratio of 0.055. And the interpretation is that given the observed data from the SUSTAIN-6 trial, a hazard ratio for the primary outcome of 1.00 is 0.055 times as likely as a hazard ratio of 0.74. Stephen Goodman, who I mentioned earlier, introduced the concept of what he called an intrinsic confidence interval to distinguish it from the usual confidence interval, shall we say. And he expressed the intrinsic confidence interval as those 2 values from a likelihood ratio function, and that curve you see on the graph is a likelihood ratio function, as those values which are 1/20th or 5% as likely as the maximally supported value. In SUSTAIN-6 data, the 95% intrinsic confidence interval is 0.54 to 1.00. The intrinsic interval is wider and apparently not as statistically significant as the 95% confidence interval. There are reasons for this, which I cannot fully elaborate on today, but a brief explanation is that the intrinsic confidence interval is based solely on the observed data, whereas I'll call it the traditional 95% confidence interval is not. Be this as it may, one thing to note is that the 95% confidence interval limits are only 1/7 or 14% as likely as the maximum likelihood estimate, and not 1/20th or 5% as likely. So I promised you a talk on meta-analysis, and this was all up to now just all sort of laying the framework of using likelihood logic to proceed in terms of meta-analysis. And I'm going to use an example from a study I led for the Canadian Network for Observational Drug Effects Studies, CNODES it's called. I apologize, but I only have time to introduce the study very briefly. A reference is provided to it at the end of today's presentation. Very briefly, we used a common protocol across the network to conduct separate studies in 6 different Canadian provinces, and in one very large American database, the US Market Scan database. And our objective, which was given to us by, that was the Canadian Agency for Drugs and Technology and Health, CADTH, our objective was to see if continuing the use of conventional synthetic DMARD therapy in RA patients after starting on a biological DMARD was associated with differences in use of biological DMARDs. And so I guess that the conventional wisdom at the time the study was done is that it made sense for RA patients who were starting a biological DMARD to also continue on conventional synthetic DMARD therapy. That's what the rheumatologists who were our consultants on the study were telling us. And so I guess there is a basis for the study that we did here. Our outcomes, which were related to the use of biological DMARDs in this study, were sort of proxy measures for effectiveness. And so we looked at discontinuation of biological DMARDs, switching between them, and the need for dose escalation over time. These were observational studies, and we used marginal structural models to obtain estimates for our associations. We then combined the estimates from the 6 separate studies in Canada and the American study using likelihood ratio meta-analysis. So Stephen Goodman wrote the seminal paper on likelihood ratio meta-analysis in the 1980s. And this is how he visually presented the method, which I have just reproduced here on some of the data from the biological DMARD study that I led. First of all, Goodman chose to display a meta-analysis on a log likelihood scale. And so rather than referring to likelihood ratios per se, he referred to log likelihood values as support units. The narrowest curve, the dark blue one, sort of in the middle, the darkest blue one in the middle, was that's the combined that if you take all the individual studies, all their log likelihood functions, and combine them, that's the combined total meta-analytic effect in the likelihood ratio analysis method. So because we are on the log scale, the log likelihood functions are added rather than multiplied. So that's one thing to note. You can multiply log values together, or sorry, you can multiply likelihoods together across studies, or if you're on the log scale, you can add them together. But I would just argue that this way of presenting a likelihood ratio meta-analysis and its component studies, while certainly conveying a richness of information, is not very reader friendly. I think you maybe hopefully would agree. And I wondered if this method might have obtained traction sooner if maybe a different format were used to present the results. This is not very reader friendly or accessible, and you have to spend quite a bit of time sort of understanding and figuring out what you're seeing. I've just added 3 red dots here, and just so I can just convey to you that from this function, you can essentially look at the maximum likelihood value in the meta-analysis. So that would be the point estimate in your total meta-analytic effect, and then the lower dots on either side would denote the 95%, traditional 95% confidence interval. The slide you see here is how we chose to present the likelihood ratio meta-analysis in our CNODES study. And I think this would be the main value add that my co-authors and I have brought to the method. And so what you see here is a familiar format now, but where the intrinsic confidence interval replaces the traditional 95% confidence interval. So we've moved away from that busy log likelihood support unit scale graph, which is less penetrable than the forest plot that many of us are used to seeing. But now the difference is that we don't report the traditional 95% confidence interval, but now we report the 95% intrinsic confidence interval. And it's a bit, the overall study was a bit complicated. We had subgroups and we looked at the different biological DMARDs. And so I'm just going to, for the purposes of today's presentation, sort of zero in on just one of the biological DMARDs now, which is adalimumab. And you can see that in this analysis of discontinuation, that for adalimumab, patients who continued on, if we look at across our studies, that patients who continued on conventional synthetic DMARDs had a relative hazard of discontinuing their biological DMARD of 0.91 compared to patients who started a biological DMARD and did not continue on conventional synthetic DMARD therapy. So on a nominal basis, at a point estimate of 0.9, it looks like that patients who continued on their conventional synthetic DMARD with their biological DMARD were about 10% less likely to stop their biological DMARD, and that fits with the notion that the rheumatologists were telling us makes sense. However, when you look at the 95% intrinsic confidence interval, it includes one, and so we would not conclude that this result is a statistically significant result. So that's taking the idea of combining likelihoods across studies and coming up with a meta-analytic result and produced in a way which is hopefully familiar to everyone. So what does the Lermid method give us versus a traditional meta-analysis? I can't go into all of the advantages that others have written or that I see. So I'll take time to simply stress the fact that the intrinsic confidence interval has I think, a more straightforward interpretation than a traditional confidence interval. And I would argue one which is more akin to how we already interpret a traditional 95% confidence interval. That's just a feeling I have. I can't prove it, but I just feel like it's something that I know is true. Not a very scientific thing to say, but I think the intrinsic confidence interval is much more in keeping with how we were mistakenly thinking of a traditional 95% confidence interval. So let me stress two things. First, the intrinsic confidence interval is a more conservative measure of evidence, and that is because it confines itself only to the observed data, and it doesn't embody any assumptions about long-run results from, say, hypothetical future studies. It's not a frequentist interpretation. And the traditional 95% confidence interval is layered with all this frequentist assumptions about long-run properties. The intrinsic confidence interval isn't. It confines itself only to the observed data, and it gives no weight to future unobserved data. And when you have less data, when you effectively have less data because you aren't giving weight to future hypothetical data, you're going to have less precision, and so you see this reflected in a wider confidence interval, the intrinsic being wider than the traditional confidence interval. The second thing I guess I would stress is that the intrinsic confidence interval is not a test statistic, and I think this is important. The traditional confidence interval is a test statistic, and it means that when you update a meta-analysis, you do not have to account for the statistical significance or lack thereof of the earlier meta-analysis with the intrinsic confidence interval, but you should account for that if you're using a traditional 95% interval as your measure of evidence. So here I show what would have happened if we conducted a traditional meta-analysis in our biological DMARD study, but pretending, for argument's sake today, that the very large US market scan portion of the data was not available when we did this analysis. the upper bound of the 95% confidence interval touches 1, and the 95% confidence interval is a test statistic. And so we do not, with this result, have the data we need to reject the null hypothesis. So I'm saying something here that you're maybe not used to thinking of in terms of a 95% confidence interval, but it is something which is derived from the hypothesis test methodology, which was put forward almost 100 years ago by Jerzy Neyman and Egon Pearson. And it's based on this long run frequentist interpretation of doing a test. It's a different way of expressing a test result, but it is nonetheless the test. And so we can't reject the null hypothesis. Now, the intrinsic confidence interval is not a test statistic. It's using only the observed data. It's still assuming a probability model underneath, but it's confining itself to the observed data and this idea that we're not necessarily looking at one fixed true underlying value, but we're trying to compare a range of plausible values. And so it has a different interpretation, and it's just denoting which values of, in this case, the hazard ratio are 1/20th or 5% as likely as the total point estimate. And that's it. So we can now sort of drive this point home with the test statistic aspect of a 95% confidence interval. We can now, let's pretend that the US market scan data have since become available, and we can update our meta-analysis with it. With likelihood ratio meta-analysis, we simply combine the likelihood from the function we combine the likelihood function from the market scan data with those of the other studies. The practice of traditional meta-analysis seems to proceed, I guess I would say in my opinion, seems to proceed in much the same way. But I question whether the 95% confidence interval retains its interpretation when it is not accounted for, when it does not account for the confidence interval, the test result from previous meta-analysis, a previous meta-analysis or multiple previous meta-analyses. And I think that's something which should be done because the traditional 95% confidence interval, as I said, is contingent on these long-run properties and not just the observed data in hand. The intrinsic confidence interval relies on only the observed data. And although both kinds of intervals still rely on a probability model, as I said, the interpretation is different. Okay, and you can see here that we have a case with the study that I led for C-nodes that the hazard ratio from sorry, not the hazard ratio, but the confidence interval for the hazard ratio. I'm sorry. There's one thing I should clarify here, which is that you see odds ratios at the top here, and that's because the graphical package I'm using here to show you this result is from RevMan, and RevMan does not, as far as I know, give a hazard ratio as an option for formatting the result, and so I just chose odds ratio, but these are hazard ratios. Anyways, the 95% confidence interval from a traditional the traditional 95% confidence interval meta-analysis shows a confidence interval which now excludes 1, and you might include maybe very, very tentatively or very not with a lot of strength of strong evidence, but we now exclude 1 from the confidence interval, and you might, strictly speaking, now reject the null hypothesis. But this is actually an interesting case where the intrinsic confidence interval still includes 1, and so you might be led to make different conclusions from the very same data depending on which one of these confidence intervals you use. Now, I just in case I haven't sold you on this idea that the 95% confidence interval is a test statistic and you should account for your previous 95% confidence intervals when you're updating a meta-analysis, let's just look at maybe a more simplistic hypothetical example where we have an experimenter having made n observations in the expectation that they might permit the rejection of the null hypothesis at a significance level of 0.05, which is very, very common significance level. used in healthcare research, that the experimenter finds this critical level was not quite attained. So the experimenter believes that the hypothesis could still be false, though, and asks how much more data would be required to have a reasonable certainty of rejecting the null hypothesis. Under this circumstance, it is evident that there is no amount of additional data, no matter how large, which would permit the rejection of the null at this 0.05 significance level. And that's because, and this maybe is news to some of you, that's because if the null hypothesis is true, there was a 5% chance of its having been rejected after the first round of observation. And to this chance, we now have to add the probability of rejecting the null after a second round of observation, given our failure to reject it after the first round of observation. And thus the total chance of erroneous rejection is increased to above 0.05. In fact, as the number of observations in the second round is indefinitely increased, the significance approaches 0.0975. Okay, if the 0.05 criterion is retained. And thus no amount of additional evidence can be collected, which would provide evidence against the hypothesis equivalent to rejection at the, sorry, I have a minus sign in there, but a rejection at the p-value of 0.05 level. Okay, so this is viewing it as a frequentist in a frequentist test paradigm. And if we do it this way, the 95% confidence interval, when we update a meta-analysis, doesn't have that, I'll say it doesn't necessarily have that 95% coverage property that we might think it has. And so we're sort of drilling down here into sort of the motivations of the researcher a little bit, but I did some digging in anticipation of this presentation today, because the Cochrane group they're basically the gold standard for doing systematic reviews, which obviously involve meta-analyses, and they also have a long history of updating meta-analyses, and I was curious to see what their approach and expectations were around updating meta-analyses, and there is this you can find that they do make reference to some sort of I won't call it a policy per se, but a rationale for updating meta-analyses, and they published a rationale recently in the BMJ, maybe not recently, maybe 8 years ago or something like that. But now this is interesting. If you go through the report, and I guess not a report, but the document dealing with this idea around when to update a systematic review in the Cochrane database, they have this is a summary of points from that article, and I'll just point out the second point to you, which says the decision needs to take into account whether the review addresses a current question, uses valid methods, and is well conducted, and whether there are new relevant methods, new studies, or new information on existing included studies. And I've highlighted a piece here for you. Given this information, the agency editors or authors need to judge whether the update will influence the review findings or credibility sufficiently to justify the effort in updating it. Now, I haven't talked to the authors of this study, but that could be interpreted as, well, if it wasn't significant before, you might want to make a priority out of updating it. And so, just words. I don't want to translate this directly into having statistical or mathematical implications, but one might look at this and say, well, maybe whether or not your 95% confidence interval for your meta-analysis was significant before might influence whether you update the meta-analysis. And then that would be directly applicable to the situation that I've told you about here with the 95% confidence interval, not having necessarily the 95% coverage properties. I just want to say a little bit about random effects. The analysis I showed you from our C-Node study was a fixed effect meta-analysis, likelihood ratio meta-analysis. And random effects, so we presented a fixed effect analysis in C-Nodes, And you might take issue with that. And actually in C-nodes, I think I've successfully advocated for us doing random effects just as a matter of practice, whether or not we feel there is sufficient heterogeneity between studies or whether each study is measuring something different. We used to drive this decision by the I-squared statistic. But we don't do that anymore, just sort of almost based on principle. And I just wanted to sort of let you know that random effects analysis is also possible in the likelihood ratio meta-analysis. And I thought I should just mention this because the way I showed you of combining likelihoods, that was really that was very mechanistic, very fixed effect. And so likelihood ratio meta-analysis is also doable with random effects. And so the fixed effect meta-analysis is based on the assumption that the point estimate from each, I say site here, we call our databases and C-nodes sites. So there's the BC site and the Alberta site and so forth. You might just, for the purposes of this, say in a randomized trial. So the point estimate from each randomized trial in a systematic review represents a statistical fluctuation around a common effect. Okay, that would be a fixed effect analysis. But random effects meta-analysis assumes that each site or randomized trial is estimating something different, at least slightly different, maybe very different or at least slightly different. And these differences might be attributable to various things: cohort entry, different study protocols, different populations, different environmental or genetic factors, and so forth. You can think of many reasons why a trial which might appear to be have done, applied very similar criteria and enrollment in Boston, Massachusetts, say, might give different results from another trial. Maybe even in Boston, Massachusetts, if they advertised for the trial in different subway lines that go to different neighborhoods. And it's not a stretch to think that randomized trials, which on the face might seem identical, might be very, very different in terms of the people who are included in them. So you want to have random effects as an option. And so when we do this, compared to a fixed effect meta-analysis where we're combining data across trials and accounting for the within trial variability when we do that, if we now think that the trials are all in part measuring something different and in part contributing information on some common underlying association, then we need to account not just for the within trial variability, but also now the between trial variability around that common underlying association. And so there's these two sources of variability. And up on the upper left here, I'm just showing you the likelihood ratio function that I showed you earlier for the SUSTAIN 6 trial semaglutide. And when I did this analysis, and by the way, you can do all of this in a Microsoft Excel spreadsheet. The graphics are harder. When I showed you the forest plot for the C-node study, that was actually used the software package R, but I actually had to trick R by recoding some of the objects to get it to produce the intrinsic confidence interval. So graphically, not easy yet to do a likelihood ratio meta-analysis, but in terms of producing the numbers and these functions, it can all be done in a Microsoft Excel spreadsheet, just as a traditional meta-analysis can all be done in a Microsoft Excel spreadsheet. Anyway, so this is the likelihood ratio function from the SUSTAIN 6 trial, and here I'm assuming a normal probability model underlying this, so a normal likelihood function, and this is just for this. So we just have this one trial here, and we can see that it looks like a very daunting equation potentially on the upper right there. Actually, if you start working with it in a spreadsheet, it's not that bad. But anyways, if we had many SUSTAIN 6 like trials that we wanted to combine in a systematic review, we could just go along the horizontal axis at each possible value of hazard ratio and multiply together our likelihood functions. And And that would produce our total meta-analytic function, from which we could then get the maximum likelihood estimate for that total effect, and then an intrinsic 95% confidence interval. And random effects can largely proceed the same way, but we just now, in addition to building in the variability in our effect estimates in individual trials, we also have to add the variability in the point estimate of each trial around some common underlying grand mean, and that's just the if you see the bottom here, just that would be represented as tau squared. So very high level here. I'm just briefly showing you this, and I realize there's maybe some potentially daunting mathematics there, but just to let you see that it's all possible to use the likelihood ratio meta-analysis method in a random effects setting. Okay, so let me get on to some take-home messages before moving on to a discussion part of today's meeting. I'll just say that likelihood ratio meta-analysis, in summary, can combine evidence from different studies. And the likelihood ratio is what we would be calling the measure of evidence in likelihood ratio meta-analysis. And we might choose to express that in the form of an intrinsic confidence interval, which is derived from the likelihood ratio function. Okay. And for familiarity, and I think this is where Goodman probably lost us back in the day, was an ease of interpretation. And so for familiarity, we can present a forest plot, which is what people are very used to already seeing with a meta-analysis. So likelihood ratio meta-analysis and the intrinsic confidence interval, as I mentioned before, produce more conservative conclusions compared to the 95% confidence interval from a traditional meta-analysis. But it has some advantages, and one is that its interpretation is the same regardless of how many times a meta-analysis is updated. We're only using the observed data. We're not using accept, reject, test statistic methodology. And here's the thing about that, is that if you're confining yourself to the observed data, the same data always give the same likelihood, and it doesn't matter how many times you look at it. So it gets over this interpretability problem with the traditional confidence interval. But the fact that it's also a more conservative confidence interval is also, one might say, more compatible with the advice of, say, Richard Peto, that a real meta-analytic effect should be at least 3 standard errors away from the null. The 95% intrinsic confidence interval isn't quite 3 standard deviations away from standard errors away from the null, but it's closer to being that than the traditional 95% confidence interval. And just to plug, in case anyone here is in the software world, it sure would be great if we could have likelihood ratio meta-analysis added as an option to existing software packages, like, for example, RevMed. I promised you some some citations for papers relevant to today, and here they are. And I think that's it for me. So, Doug Chiprin, I'll hand it over to you to moderate any questions that we might have from the audience.
Thanks, Colin. That was fantastic. And we've had a bunch of questions come through in the chat from Valerie King. She's asking, it would be helpful to know when this method would be the most appropriate method to employ.
Yeah, so I'll just say probably most of my responses here for this sort of question would be, in my opinion. I can't think of a case where you wouldn't want to use this method in favor of a traditional analysis. Like it, to me, I feel if someone takes the time to think about it, maybe read Goodman's paper, maybe read my paper in Contemporary Clinical Trials. I feel once you understand the method, I would challenge you to figure out why you wouldn't want to use it in favor of what we're doing now. Hopefully that answers your question. I can't think of I just can't think of a situation where you wouldn't want to use it and you would want to use, the traditional methodology.
Thanks, Colin. And we had a question from, and I'm sorry if I'm butchering your name, Per Litsi. Is the ICC a better interval for determining the whereabouts of the true parameter as compared to a confidence interval?
So that's a good question. That might be, but I guess I would, for that question, I would really bring it back to the conceptual framework of whether we're viewing this as some true fixed underlying value. And I don't know what implication the ICC has for that conceptual framework. But I will say that the intrinsic confidence interval is one way to use to take the result of a likelihood ratio methodology and work towards some sort of statement of strength of evidence, which is essentially what it's doing. I would think with ICC, you would still need some sort of index around which to say something is constitutes weak evidence, moderate evidence, strong evidence, or very strong evidence.
Thanks, Colin. And we have a question, a couple of questions from Theodora and Gulva. The first one is the interpretation of ICI seems less obvious as traditional confidence intervals, and this might confuse readers. Are there specific guidelines regarding its use and interpretation within Cochrane?
So I find that a very interesting comment or question, because I find the interpretation of a confidence interval to be somewhat the real interpretation of a 95% confidence interval to be somewhat abstract. And so if we're applying this frequentist paradigm, long run properties, then the idea would be that in a clinical trial with a 95% confidence interval, you actually don't know if that 95% confidence interval has captured the true underlying fixed unknown effect or not. You would have to do many randomized trials with many 95% confidence intervals. And if you did a lot of these things, say 100, you would expect 95% of your 95% confidence intervals to capture the true underlying fixed association. But in any given trial, you would have no idea whether or not that's the case. Now, if you then take, and that's just for one trial, if we then take that sort of logic and then put it into a meta-analysis where we're talking about different trials, I have a hard time even conceptualizing what a 95% confidence interval in a conventional meta-analysis even means. So I guess, sorry, I didn't catch the name of the question here, but I guess I disagree. I find it very convoluted to think of a 95% traditional confidence interval in a meta-analysis. And that sort of goes to my point where I said the intrinsic confidence interval, I think, is the interpretation that people are probably mistakenly giving to the conventional or traditional 95% confidence interval.
Thanks, Colin. And the other part of her question was just asking about if there are specific guidelines regarding its use and interpretation in Cochrane, which I know there's some references to its use in the DTA handbook, which people have access to if they're Cochrane members. But I don't know if you're aware of specific guidelines regarding its use. I'm not.
I gave a presentation similar to this one at the Cochrane colloquium in September. I'm hoping to get some more traction for using the method, but I somewhat humbly have to say I think I'm the only one. I think I'm the only one who's actually applied this in a real world setting so far. And I could be wrong about that, and I hope I'm wrong about that, but it's something that still needs to get off the ground. It would be great if Cochrane would consider some of these issues, and maybe even, and I don't mean this in any way to be critical of the people who have thought about when to update systematic reviews in Cochrane, but it would be really, I think, really fruitful for there to be a discussion about this issue. And is the 95% confidence interval a test statistic? It is. Therefore, if it's a test statistic, you should use it that way, and that has implications for how you interpret the confidence interval in a subsequent updated systematic review. And so Doug, as you know, I'm interested in this and would be happy to be included on any forum that Cochrane might convene on this or similar issues.
It would be interesting to see this presented again at the next Cochrane colloquium, or next year it will be called the Global Evidence Summit, which will bring people together from other organizations such as GIN and the Campbell collaboration. So hopefully you'll submit this again.
Yeah, I wanted to do a workshop actually where we sit down and I could actually, people could actually do a likelihood ratio meta-analysis. I'd show them the conventional way, all in a spreadsheet, and just in a workshop forum, walk people through being able to do it, and then that might get people using it. It hasn't so far been, this one study. It wasn't rejected. It wasn't a source of contention amongst reviewers. Obviously, when you submit a paper to a journal, there are many comments from reviewers that you have to deal with. But the fact that we use this method was not controversial to the reviewers, and if memory serves, not even to the statistical reviewer.
A follow-up question from Theodore: is there an R package using the likelihood ratio method that you might be aware of?
There might be. There was when we did the C-Note study, there was a student in Quebec with the Quebec team that was doing the analysis, who took an interest in the method and was apparently going to write an R package. And I actually haven't checked if that's actually been posted. I maybe should have, but so there is someone who was intending to, and so that's good news. And whether they actually did, I would need to check. As I said, I used R to produce the forest plots in the C-Notes paper that we published, because I just couldn't. I couldn't get. I prefer using RevMan, but I just couldn't get it to behave in the way I needed it to produce the right rendering of the forest plot.
Tajani is asking, can you elaborate what you mean by the message of being 3 standard errors away, and why is this a good thing?
Yeah, I think I gave a reference to Peto's paper there, and but just to expand a little bit more on Peto's logic is that I guess I will. One thing I didn't say is that he was basically referring to this idea that a meta-analysis might be done because there's, say, a drug that might end up being used by thousands or millions of people. I don't remember the exact phraseology he used. And that's pretty serious. If there's a drug that's going to be taken by a lot of people, then the amount of evidence you should require in that situation should be really strong. So, and I think he suggested something like three standard deviations. And I'm sorry, Aaron, I can't really convey a whole lot beyond that. But I'll just, while we're on the topic, I'll just remind you that I showed you a slide earlier that showed that the 95% confidence limit values, hazard ratios, odds ratios, whatever we're looking at, aren't 5% as likely as the point estimate. They're 1/7 as likely, or 14% as likely. And so even if you just look at it in relative likelihood terms, the 95% moniker doesn't even mean anything. It really is this long one, frequentist assumption of doing a randomized trial many times, which no one does. That leads to this the 95% moniker in the traditional confidence interval.
Aaron's asking as a follow-up, is it a measure of how meaningful the evidence is 3 deviations away?
Well, so that's where so you can be really quantitative and statistical and mathematical up to a point. But as soon as you take a number and you refer to it as being weak or moderate or strong or very strong, that right there, you're putting a subjective layer on that. And so I mean, I think where that comes from, and I'm just guessing here, is a convention which is developed over the year, where if your 95% confidence interval excludes the null, you might have moderate evidence, might be the convention. That might correspond to a p-value of 0.05. I guess it does. But if you had a p-value of 0.01 or less, then that would be very strong evidence to say just by convention, but just subjective. And I guess I can only refer you to just how things have developed by convention over time.
Aaron, I see you've got a follow-up question. Colin, was just about confidence intervals that overlap 1.0 for safety outcomes. And this question is coming from Tom Perry.
Again, I would think this is a matter of convention and opinion that, you know, if you just take the sort of the generic case where you have a primary outcome from a trial or a systematic review, which is on some clinically meaningful outcome that you think might be the benefit of the drug. So say a cardiovascular outcome. When you think there's a protective estimate, and maybe that's significant at a 5% level, that's one thing. But if in, say, a secondary outcome or serious adverse event data, you see that the point estimate for mortality has gone up on the drug, well, you might, whereas for benefit, you might want to expect very strong evidence for that in order for this drug to be used by lots of people.
Thank you again so much, very much, Colin, for this presentation, and thank you everyone who attended.